Welcome to the presentation on Global Review on Shale with focus on hydrocarbon geoscience and carbon sequestration. Based on research conducted by Ankita Paul, Soumyajit Mukherjee, and Mery Biswas, published in the journal Results in Earth Sciences, in the year 2025. In the upcoming slides we will explore the importance of shale gas as an unconventional resource, factors which govern the commerciality of shale basins. Shale rocks have acted as important resource for energy crisis around the world, being an unconventional resource of hydrocarbons. Not only this, shale basins have also emerged as one of the best geological sites for carbon capture. Due to their very low porosity and permeability, researchers have regarded them as good storehouse for carbon sequestration. With improving research, technology and methodology for transferring atmospheric carbon dioxide, we will see the level of carbon dioxide go down due to carbon sequestration. This would improve the global warming scenario of the globe. CCS or carbon capture and sequestration, or simply carbon sequestration, refers to the process of capturing, transporting and storing carbon dioxide from the atmosphere, intending to mitigate climate change. Carbon dioxide has been a major effluent from industries, power plants and fossil fuel combustion. Capturing carbon dioxide and storing it in large reservoirs underground can help cut off its contribution to the atmosphere, clean the gas we inhale and contribute to lowering global warming levels. The world contains 50 to 65% of shale in the sedimentary record. It is considered an important source of unconventional hydrocarbons and acts as a source or reservoir. Due to its low porosity and permeability, it has emerged as an important rock for storing carbon dioxide and contributing to lowering the levels of carbon dioxide in the atmosphere. Several factors on which carbon sequestration depend on are: 1. Total organic carbon. The adsorption rate of carbon dioxide is directly proportional to the amount of total organic carbon present in the shale rock. 2. Permeability and the type of pore spaces. 3 types of pore spaces are present in shale. 1. Within organic matter. 2. In between the mineral grains. And 3. Pore spaces within discrete mineral grains. Nano and micropores as well as fractures in shales act as best site for storing hydrocarbons or for carbon sequestration. 3. Geological reservoir setting. Post-rift basins, extensional passive margins and compressional fall-in basins are the prime geologic reservoir settings for carbon capture or storage. 4. Time. The time required for carbon sequestration process depends on mineral dissolution and precipitation in the rock system. 5. Diagenesis and depositional site characteristics. Shale is a fine-grained sedimentary rock having a grain size of less than 4 micrometers. It is dominantly made up of clay minerals, mostly light, framework silicates, carbonates, sulfates, and organic matter with or without fossils. An important characteristic seen in shales is its fissility. Black shales are dark organic rich mud rock with more than 1% organic carbon. They are typically enriched in vanadium, arsenic, molybdenum, lead, copper, nickel, zinc, and uranium. They are formed in quite suboxic to anoxic environment, with oxygen-deficient conditions. Not all organic rich shales generate hydrocarbons. Since shale has very low porosity, usually 5%, and ultra-low permeability of 100 to 1 millidarcy, hydraulic fracturing and horizontal drilling becomes important to extract hydrocarbons from them. Shales containing clay to silt-sized grains form in calm depositional environments, where the flow of water is ceasing, or in environments where the basin is free from any natural disturbances. Some of the important depositional settings of shale are: 1. Calm and shallow water bodies where the circulation of water is stopped for some reason. 2. Continental setting, swamps, bogs and lake environment. 3. Marine shales which form inside deep oceans, often in anoxic conditions resulting into black shales. 4. Nearshore environment during long periods of quiescence. Other settings include formation of shales in roofing slate layer in between coal seams, black shale formations in fjords or geosynclines. Supercritical carbon dioxide is carbon dioxide at temperature and pressure of more than 31.1 degrees Celsius and 7.38 megapascal respectively. It has the capability to replace hydrocarbons from shale organic materials. Such a process changes the microstructure of shale. In an independent study, it was revealed that supercritical carbon dioxide reduces compressive strength and elastic modulus of shale and brings about long and short-term chemical changes in it. Supercritical carbon dioxide fracturing leads to more complex and rougher fractures than hydraulic fracturing and produce greater permeabilities. However, chemical changes alter the reservoir property. Through numerical modeling, it was proved that as the stress sensitivity coefficients, indices of adsorption and Knudsen diffusion elevate, the carbon dioxide storage capacity in shale reservoirs increase. Large areas of surfaces in shales have greater capability of adsorption of carbon dioxide. In case of physical adsorption, carbon dioxide is contained within the structure of the shale. On the other hand, in chemical adsorption, carbon dioxide is attached by chemical bonds. The latter has a reduced risk of leakage. Understanding the physical extent, reservoir characteristics, commercial viability, and carbon capture and storage potential of shale and shale plays is essential for comprehensive shale basin characterization. Shale samples have been collected from basins and other sources, through drilling or field work. Methods for assessing such parameters are optical microscopic analysis of thin sections, for assessing the mineralogy and petrology of shale samples, spectral gamma-ray log, for analyzing clay mineralogy, geochemical, depositional environment and the thickness of the shale formations, scanning electron microscope energy dispersive X-ray analysis for identification of the characteristics of organic porosity, X-ray diffraction for mineral phase identifications at relative intensities and scanning range, X-ray fluorescence, to assess the concentration of major oxides in shale, total organic carbon, to assess the degree of organic richness in the sample, Tmax index, which determines thermal maturity of the source rock, vitrinite reflectance, for assessing thermal maturity, organic pore size determination, for knowing the character of pore spaces present in shales, rock eval pyrolysis, Fourier transform infrared spectroscopy, in which the pyrolysis determines the decomposition zones of the shale sample and investigates thermal degradation, seismic inversion studies, that produces the geological structure of a basin from seismic data and well-logged data through subsurface modeling, hydrocarbon saturation, that suggests the best patch for hydraulic fracturing, X-ray computed tomography. It provides 3D data geometries and properties of the solid shale reservoirs in different scales. Young's modulus, capillary suction time, which states the nature of the shale mainly applicable during reservoir drilling, and entropy weight method. There are 52 countries around the globe that contain 108 established shale basins and 156 formations for commercial oil and gas exploration. For commercial development of shale basins, factors that are crucial include thickness of the shale formation and their depths, low permeability of the caprock or seal, and geochemical and hydraulic properties of potential organic rich source rocks. When considering the carbon sequestrating capacity of the shale formations, it varies for different formations. The figure shows the location of the world shale oil and gas basins using ArcGIS platform and Google Earth Pro, and the global risk-in-place recoverable shale oil resources. Carbon sequestrating capacity of various shale formations have been studied, but some still don't hint into being a good storehouse of the greenhouse gas carbon dioxide. Let's take a look at some specific examples of countries to know about the global scenario of hydrocarbons in basins of the world with their carbon capture capacity and the processes that have led to locking up of carbon dioxide in them. China. China holds the world's largest shale gas reserves, with 7 key basins including Sichuan, Yangtze Platform, and Jianghan, Subei, Tarim, Junggar, and Songlao. Marine shales, particularly in Sichuan, show high maturity and strong gas potential. In Sichuan, carbon dioxide entrapment has occurred since Cambrian through thermal and biological processes, especially by algae in deep anoxic marine shales. In the Jianghan Basin, carbon dioxide is stored in deep saline aquifers and migrates through fractured cap rocks. However, carbon sequestration studies in the Tarim Basin remain limited. Russia. The West Siberian Basin is the largest petroleum basin in Russia. The oxygen-carbon-rich siliceous shales of the West Siberian Basin are the potential source rock of hydrocarbon production in Russia. Data for carbon sequestration is not available from the Russian basins. The Rub al-Khali Basin is the most significant shale oil and gas prospect in the United Arab Emirates, with source rocks from the Qusayba, Diab, and Shalaif formation. Formations dot the lower Silurian Qusayba hot shale, located at the base of the Kaliba formation, formed in an anoxic marine setting, making it rich in organic content. The region also holds considerable potential for geological carbon dioxide storage, particularly in Saudi Arabia's depleted oil and gas reservoirs. Structural features like the Wajid Graben, formed during the Ediacaran to early Cambrian extension, further enhance the region's storage and exploration prospects. Pakistan. Pakistan is grappling with growing energy demands due to its rising population. The southern and central parts of the Indus Basin are the main targets for shale oil and gas exploration. The Lower Cretaceous Sember Formation, deposited in an open marine environment, serves as the primary source rock. In terms of carbon sequestration, tight carbonate formations within the basin, although having low porosity of nearly 3%, show potential for long-term carbon dioxide storage. These resources offer strategic importance for meeting the country's future energy and climate goals. India. India has 4 key shale basins, Kempe, Krishna Godavari, Damodar Valley, and Gondwana, with 96.3 trillion cubic feet of shale gas and 3.75 billion barrels of shale oil. Of them, the Krishna Godavari Basin shows evidence of natural carbon sequestration. The presence of gas hydrate and coal seeps in the basin were identified from the topographic mounds by the multi-channel seismic data from the National Gas Hydrate Program 1 expedition. Gas hydrates were found to be captured in fractures and the fossils in the form of carbonate nodules. The carbon isotopes of the samples portrayed the history of natural sequestration of carbon in the basin. The sulfate from degraded organic matter and methanogenesis produced carbonate in the basin. Additional prospects include Upper Assam, Pranhita Godavari, Vindhyan, and Rajasthan basins, offering strong energy and storage potential. Oman. Oman's shale basins, South Oman Salt, North Foreland, and Rub al-Khali, formed due to Gondwana breakup. The Fahud and Ghaba salt basins are most promising for unconventional hydrocarbons. The Rub al-Khali features thick sedimentary sequences and conditions favorable for carbon sequestration due to Paleozoic tectonic activity, deglaciation, and sea level rise. Indonesia. Indonesia hosts extensive shale oil and gas resources formed in the lacustrine setting during the Mesozoic and Cenozoic eras. The top 5 prospective basins are Central Sumatra, South Sumatra, Kutai, Tarakan, and Bintuni. These basins are rich in organic content and hold significant potential for hydrocarbon exploration and carbon storage. Kazakhstan. Kazakhstan's major hydrocarbon basins, North Caspian, South Mangyashluk, South Turgay, Chusarisu and North Ustat, are located in the west. The country is a key oil producer with promising formations for carbon dioxide storage, including saline aquifers, depleted reservoirs, and unminable coal seams, all found within extensive sedimentary basin systems. Mongolia. East Gobi and Tamtsak are Mongolia's key thermally mature shale basins, formed in fluvial lacustrine settings during the Jurassic Early Cretaceous. The East Gobi Basin is oil-prone in deeper areas. Thailand. Thailand has not yet explored its shale resources despite high potential. The Khorat Basin is considered one of the most promising shale gas prospects globally, with the Namduk Formation identified as the main target for future shale gas development. Both Mongolia and Thailand do not show any information on carbon sequestration process in the countries. Next, Algeria. Algeria's key shale formations, Tanazout and Frasnian, span 7 Paleozoic-formed basins. Structural traps and heat flow events aided carbon sequestration. The Timimu Basin's Silurian shales are rich in dry gas, and thick Jurassic sediments sealed by salt beds further enhance storage potential. South Africa. South Africa's Karoo Basin hosts extensive black shales from the Pennsylvanian Jurassic period. These organic-rich deposits were altered near igneous intrusions, converting shale into graphite and carbon dioxide. While promising, thermal alteration affects both hydrocarbon potential and carbon storage feasibility. Chad. Chad has 6 key hydrocarbon basins, Termit, Bongor, Dob, Doseo, Salamat, and Irdiz, Kufra. These intracratonic basins hold significant shale oil and gas potential, making Chad a promising area for exploration in Central West Africa. Tunisia. Tunisian black shales form due to transgression from glacial melting or tectonics. Ghadames and Pelagian basins are the country's main hydrocarbon prospects, with strong potential for shale oil and gas exploration. Argentina. Argentina has the most potential and large shale oil and gas reservoir. In South America, the Neuquén, Golfo San Jorge, Austral and Parna are the 4 significant sedimentary basins assessed for commercial shale oil and shale gas exploration. Brazil. Brazil has 18 sedimentary basins, among which 3 are the most significant and potential large shale rock reservoirs with prolific commercial shale oil and gas. The Devonian black shales deposited in the marine environment of Paraná, Solimões and Amazonas basins are the main targets for shale gas and oil exploration in Brazil. Colombia and Venezuela. The Middle Magdalena Valley, Llanos basins and the Maracaibo or Catatumbo basins are the 3 most potential reservoirs for shale oil and gas of the northern South America. The basin consists of Cretaceous organic-rich marine deposits. Bolivia, Chile, Paraguay, and Uruguay. The 4 countries in South America share 3 large prospective shale basins for shale oil and gas exploration. The shale formations in the basin are marine deposited sediments in the Cretaceous and Devonian periods. Mexico. Mexico has huge shale gas and oil reservoir along its onshore Gulf region. Mexico with large storage of shale gas and oil in its marine deposited shale, which correlates with notable Jurassic and Cretaceous hydrocarbon-rich shale deposits of the Eagle Ford and Haynesville shales. Maximum oil and gas field is found in the narrow coastal area, which has conventional Miocene and Pliocene sandstone reservoirs. The genesis of hydrocarbon is associated with the compressional and thrust faulting during the evolution of the Sierra Madre ranges, when the narrow coastal plain of Mexico was squeezed and created a chain of discontinuous subbasin. The Burgos, Sabinos, Tampico, Tuxpan Platform and Veracruz basins are the most prospective shale gas and oil exploration targets. Canada. Canada hosts numerous shale basins. The major shale oil and shale gas basins in Western Canada include Horn River Basin, Cadova Embayment, Liard Basin, Doig supergroup of basins, Colorado group of basins and Montany subgroup of basins, with an estimated 28 trillion cubic meters of gas in place. These basins formed in anoxic to ionic marine settings with high organic matter, which over millions of years transformed into hydrocarbons. The organic-rich shales have significant potential for carbon dioxide sequestration and climate sustainability. Other prolific basins from the eastern side of Canada include Appalachian Fold Belt and Windsor Basins. Australia's shale plays, including Cooper, Maryborough, Perth, Canning, Georgina, and Beetaloo, span from the Proterozoic to the Cretaceous. Influenced by periodic glaciation and Pandalasan ocean upwelling, these basins developed organic-rich shales like Sydney and Bowman formations. This geological setting favors shale oil and gas accumulations alongside opportunities for carbon capture and storage. Europe. The Eastern Europe consists of Bulgaria, Romania and Ukraine with three potential basins, Dnieper-Donets, Carpathian Foreland and Mesian Platform. Of these, the marine shales of Carpathian Foreland Basin provide suitable sites for the chemical entrapment and storage of carbon dioxide due to their high organic matter content. Coming to North and Western Europe. Poland has four prospective shale oil and gas basins including the Baltic Basin or Warsaw Trough, Podlaskie Depression, Lublin, and Four Sudetic. The basins are highly porous and brittle with low clay and high quartz content. Of these, maximum carbon sequestration through adsorption is reported from the Baltic Basin. United Kingdom. It is the country with the second largest oil and gas potential with extensive stratigraphic sequence of organic-rich shales. The older shales are mature and contain thermogenic gas, whereas the shallower and younger shales are conventional hydrocarbon source rocks containing biogenic shale gas. Carbon sequestration in the Weald Basin started from the early Jurassic. France. It includes the two promising shale oil and gas basins, the Paris and the Southeast Basins. Carbon sequestration occurred when the Lower Jurassic White Lias, Lower Lias, Middle and Upper Lias strata were deposited as a result of the Lower Jurassic Retic transgression, which was caused by thermal subsidence linked to a block faulting during the mid-Mesozoic era. Germany. The Lower Saxony Basin in northwest Germany is the main hydrocarbon reservoir of the country. Tectonic forces generated hot hydrothermal fluids that were overpressured during the late Cretaceous inversion of the basin, supplying a substantial volume of carbon dioxide. Fluid inclusions have been recorded in minerals from fracture-filled mineralization in the Devonian and Upper Carboniferous period. Deeply buried Devonian sequestrated carbonates have experienced a high-temperature metamorphism, which released carbon dioxide that rose through deep-reaching faults. There has been a close link between deposition of black shales during Lower Cretaceous and methane hydrate dissociation and extensive igneous volcanism. One of the most important outcomes of global driving mechanisms that worked throughout Cretaceous was the deposition of carbonate sediments. Their deposition has been closely related to an anoxic period and hence black shale deposition. Asia includes 4 countries: China, India, Kazakhstan, and Indonesia, and with 12 basins containing black shales. As we have taken a look around the global scenario on shales, their importance as unconventional source of energy, we see that 5 basins with black shale formations have proved significant in terms of recoverable resources: Paraná Basin, Argentina; Solimões Basin, Brazil; Jianghan and Greater Subay Basins, China; Amazonas Basin, Brazil. As we come to end of our presentation, let's conclude the following important points. Shale formations are major sources of unconventional hydrocarbons, with significant variation in total organic carbon, vitrinite reflectance, thickness, and depositional settings. Most hydrocarbon-rich shales have deposited between the Cambrian and Cretaceous periods. The depleted shale reservoirs offer promising sites for carbon dioxide injection and long-term carbon sequestration. There has been a rise in the demand of carbon sequestration and shale as an unconventional resource. Problems faced in carbon sequestration include geological complexity of reservoirs, technical challenges and advancements, environment and safety concerns, and geopolitical issues. As we are at the end of the presentation, I hope this discussion would have helped you understand the importance of shales and their significance to carbon capture and storage. The research paper, Global Review on Shale with Focus on Hydrocarbon Geoscience and Carbon Sequestration, examines shales, their formation settings, and their rising importance as an unconventional energy resource and storehouses of carbon. Carbon capture and storage is an essential matter getting studied by several nations to reduce greenhouse gas emissions, especially carbon dioxide, which contributes to global warming. Thank you for your time and attention.